The lithium-ion battery has changed our lives over the past 20 years and made the digital revolution of the 21st century possible. It's rechargeable, it lasts longer and is more powerful than a conventional battery. The mobile world lives and dies with lithium-ion batteries because there's no other rechargeable energy store that's currently even close to matching it.
Mobility only became possible thanks to lithium-ion batteries, be it in communication or in transport.
The lithium-ion technology is also important for the future of electromobility, because without batteries there won't be any electric cars.
Our vision is to design a battery that makes a range of 700 kilometers possible, but that's far off in the future.
Last year, 5 billion lithium-ion batteries were sold in laptops, cameras, phones and electric cars.
I think there's a lot of room for improvement still in lithium-ion batteries, particularly with regard to capacity. That means they can really help with the range of electric cars. On the other hand, a lot of work is needed to make the material safer.
Battery research is focusing on increasing capacity, efficiency and lifespan, and reducing the weight and cost.
The important question for us scientists is, why does one cell work so well and why does another cell that looks the same but has a different chemistry work differently?
To achieve all of that, we need to take a close look at the battery's interior.
In many cases, it's optimization that increases capacity and stability.
The battery's performance could be increased through new materials, for example. At the University of Salzburg, the Department for Material Chemistry is developing and producing new materials for lithium-ion batteries. A rechargeable lithium-ion battery consists of a positive and a negative electrode and a separator, which prevents a short circuit. During the charging process, positive ions move through the separator into the negative electrode. The better the ions can move, the better the battery's performance.
It's like this. In modern batteries or lithium-ion cells, the lithium ions have to move from one electrode to the other. They have to be able to exit on the other side without the structure there impeding the positive electrodes, for example. These ions must be able to come and go without massive changes in the structure. And they mustn't make the electrode much bigger.
The main goal is to manufacture very small materials that exhibit a large surface area so that as many lithium particles as possible can be accommodated.
That means we're using methods where we add molecules that inhibit growth. We try to get very small particles that maybe have a molecular shell to protect the whole thing.
One promising material that's being tested here is silicon, which accommodates a very large number of lithium ions. To avoid changing its reaction, it's treated in a glass box where there is no oxygen and no liquid.
Silicon is a material that can be used as a negative electrode. Compared to graphite, it has the advantage that it can accommodate a greater number of lithium ions. Chemically speaking, the problem with silicon is that it expands a lot when it takes on the lithium ions. A lot of research is going into keeping this expansion under control.
But when one part of the system is changed, all the others need to be adapted.
If I were to take a new material for the negative electrode, that would mean that all the other materials in the battery cell would have to be adapted. The electrolyte would have to be adapted. The positive electrode would have to be adapted. It doesn't help just to get a lot of lithium into the silicon electrode. It has to come from somewhere.
The materials made in Salzburg go to the Austrian Institute for Technology, AIT for short, where they're built into a battery in a joint project before being analysed in a battery testing lab.
We're looking at cell components. We're focusing on the active electrode materials, on cathode and anode materials. We're trying to optimize the existing cell chemistry, and we're also developing new components and new materials for the next generation of lithium-ion batteries.
The scientists get a close look at the properties of the materials.
With regard to the chemical characterization, we're interested in the structure of the materials, the morphology, and the nature of the surfaces. We want to know about particle size and the distribution of the different sizes overall. These are the methods and parameters of materials that are very important for a lithium-ion battery.
They make prototypes here. Graphite is mixed into a slurry that is applied to copper or aluminium as a current collector. After that, the electrodes are dried and pressed in hot conditions. They are punched out and made into button cell batteries.
The prototypes are only for our research. But we offer the service of running battery tests in our lab. The lab is accredited, and we test according to ISO norms. And we use the protocols that are relevant to us and to battery manufacturers.
The most important aspect of battery research is safety. Exploding mobile phone and laptop batteries have resulted in negative headlines in recent years. Boeing's Dreamliner had to stay grounded for quite some time after batteries caught fire in the air. That's obviously extremely undesirable. As a result, the AIT tests batteries for their suitability for everyday use. There are many high-performance materials, but many of them could be quite dangerous.
We perform electrical tests, characterizations, lifetime performance tests, driving cycle, and things like that. We also do misuse tests. We test the cells to see how they react to certain things.
A battery is prepared for the nail test under the strictest safety precautions. It's taken to a specially prepared chamber fitted with temperature and pressure sensors. Cameras will record the whole process. This way, the events can subsequently be scientifically analysed. In the nail test, a 3mm nail is driven completely through the battery.
Usually the cells release gases or nothing happens, or else they become inflated, or the electrolyte leaks. The worst case would be an explosion. We're destroying the cells in a controlled manner, so we get useful data.
For other tests, the battery is overcharged, dropped, squashed, or short-circuited.
You want to classify the cell's reaction into levels. It can range from nothing all the way to an explosion or a fire. You might just see smoke or electrolyte emerging. It varies. But usually the worst that we see in batteries ready for production is a little smoke.
A lot of data is logged during the tests, such as temperature, force, and voltage. The batteries are also exposed to the cold, to dampness, dust, and salt. They're charged up and emptied to see how durable they are. Simulating battery aging is one of the focal points at the Christian Doppler lab in Graz. The scientists here examine in detail the charging conditions and the irreversible changes in the life of a battery.
You can examine individual components and materials with regard to aging. You can examine this electrochemically while the battery charges and empties.
One example of this is cyclization. Charging from 0 to 100% is one charging cycle. The scientists test how often a battery can be charged, why it loses capacity during charging, and how it reacts to different voltages and temperatures.
The other option, along with many others, is to test the battery's current load. The battery is charged very quickly or very slowly, in seconds or in an hour. That has an impact on the capacity of such a battery. The goal is to develop batteries that can be charged as quickly as possible.
At a post-mortem analysis, the broken battery is taken apart.
You can then see if there's been irreversible damage, if the separating components are intact. And you can draw direct or indirect conclusions about the stresses the battery underwent. Then you can make forecasts about batteries in a similar state of health and how they can be charged and emptied, and at what temperatures and operating conditions this charge is still usable.
Research in the area of lithium-ion batteries has developed massively in recent years. That too has resulted in a lowering of prices. 5 years ago, a kilowatt hour still cost around €1,000. Today, it costs 250. The goal is to get the price for 1 kilowatt hour to below €100. Lithium is as sought after as oil and could become increasingly important for the future of electromobility.
Mobility will become attractive when the costs of the battery pack come down, because that's the biggest expense of electric cars. The consumer also wants safety and range. As soon as more such vehicles are on the streets, the acceptance of electrical vehicles will go up.
In electric vehicles, the electric energy in the lithium-ion battery is transformed into mechanical energy. The electric vehicles with the greatest range right now are made by Tesla. They can travel up to 500 kilometers under normal driving conditions. The performance of electric vehicles is incredible. They can accelerate from 0 to 100 kilometers per hour in 3 seconds, producing zero emissions. When it comes to electric mobility on 2 wheels, Austria is already a major player. The Johammer company has built the world's first production electric motorcycle. It has a range of 200 kilometers. The Electro Cruiser J1, Austrian design, development and technology.
There were 3 principles that didn't come from us, but from a Swiss design engineering team. A small batch size that was financially viable, 100% recyclable, and maintenance-free. Conventional wisdom would say those are 3 knockouts.
The electric motor has a nominal output of 15 horsepower. Its top output is 22 horsepower, enough for 120 kilometers an hour.
Cruising around, traveling, mobility. It's a good thing. Electromobility is relaxing, and that's why the marketing also positions it as such. Others don't have this good range. We knew we had to develop the battery ourselves because there wasn't one on the market.
When designing the product, the type of cell had to be set right from the start, because the battery is developed around it along with the drive electronics. The finished battery, weighing around 70 kilograms, consists of 1,200 individual lithium-ion cells. A special laser welding process is used to assemble them.
It was an additional obstacle to develop that, but we knew that if we didn't master this technology, then we would be missing the heart of the entire concept.
Gesamten Kompetenz. Ja.
The company's current plan is to build 50 motorbikes a year. The models cost up to €25,000, depending on the battery capacity. Of course, the company wants to achieve greater ranges. As a result, the battery is easily exchangeable.
From that emerged a new idea that we would take back these batteries that were still new, really, and that we would use them in a second life. For example, in home applications.
The batteries are currently able to undergo 2,000 complete charging cycles. That's around 250,000 kilometers driving pleasure. One challenge for the entire electric vehicle industry is charging times.
At the moment, the charging period is 3.5 hours. Next year, that'll be 80 minutes. It depends largely on what's possible in the grid. It makes a difference if you're connected to 220 volts or 380 volts. Next year, your Hammer will be able to do it all, regardless of the connection. We'll take anything.
Charging concepts are a huge issue because electric recharging stations have to look completely different from conventional petrol stations. It won't be possible to charge up more than 10 to 15 vehicles per hour. There will be longer charging periods and charging spots are elaborate and expensive.
When we refuel at the moment, we're transporting energy from the pump through the hose to the tank. That's 10 megawatts of power. When you charge a battery, we're talking maybe 50 kilowatts. Our normal domestic connection has 10 to 12 kilowatts. If you want to charge an electric vehicle at home, you have to charge it for a minimum of 5 hours, because that's all the power you have available. If you want to charge it in just 1 hour, you need 5 domestic connections. If you want to charge it in 10 minutes, you need 60.
This is one of many issues transport experts and the automotive industry have to think about. They also have to ask how sustainable electromobility really is.
But if it's to be green, you have to be careful when you want to balance the books with regard to raw materials. Is it competitive and ecologically defensible compared to vehicles that are still working with combustion engines?
Almost every major car manufacturer around the world is currently investing in research. The demand for electric vehicles is growing.
What we've been seeing in recent years is a small but steady increase in the share of electric vehicles. We're expecting that to increase in the future. But it'll still be a niche thing in the next few years. They won't be as dominant as diesel and petrol vehicles.
And that's directly associated with the future of the battery. If customers can be given the range and power they want, the trend towards electric vehicles will grow significantly. Time and again we hear from the industry and from research institutes that the super battery has been found.
There's a grain of truth in that because, in theory, you can get a lot out of the systems. The problem is, if you look at the system as a whole, the entire battery pack, then there's a lot of electronics in that, and a lot of safety measures that get in the way of these theoretical energies. And then you're left with half.
In addition to lithium-ion research, labs are also feverishly working on new materials for future battery generations. Lithium air systems and lithium sulfur cells are two promising approaches.
We expect to be able to travel 500 kilometers with this system. But this technology is still at the basic research stage. Some time will pass before it's ready for market. Maybe 20 or 30 years. Another technology with a different potential is the magnesium-ion battery we're researching.
It's a fact that as long as global energy consumption is on the increase, the storage of electrical energy will be the big topic of the future.